I guess we're going to go over an example just to exemplify how the Lyapunov functions work, how the theory works. And yeah, so we're going to consider the pretty much prototypical example that we've been considering all semester, namely the pendulum example. Let me turn on this light. Maybe it'll be better. Great. So, so this example is from Khalil's book, the third edition of Nonlinear Systems. That's Hassan Khalil. It's a really good reference for control engineers, for system dynamicists. Provides a lot of information for general nonlinear systems. And again, anything for nonlinear systems is also applicable to linear systems, which is a subset. So in this example, we're going to consider the pendulum. Equation. And in this case, we're going to look at the pendulum without friction. Okay, so in particular, these dynamics are given by x dot is equal to x2, x1 dot is equal to x2, and then x2 dot is going to be equal to minus, let's say, a sine of x1, right? So in previous classes, x1 and x2 are just the angle and angular rates, respectively. Jack's there causing a ruckus. And then A is the gravity forces, right? So what we want to do is we want to study, period. So we want to study the stability of the equilibrium. Point at the origin. Okay. So one simple function that we can use for this. So I mentioned last time that one good place to start is either a quadratic equation or the energy of the system. So we know in natural systems, energy tends to dissipate. If there's no energy being pumped into the system, entropy tells us that energy must go somewhere. Usually it goes out through heat or actually heat, friction, some other non-conservative force. So in this regard, a natural Lyapunov function is the energy equation for this pendulum. All right. So we're going to consider V, or the Lyapunov function, is equal to A1 minus the cosine of theta, or not theta, x1, plus 1/2 x2 squared. Okay, so this guy right here is the potential energy if you want to map it to somewhere, and this guy right here is the kinetic energy, components of the energy equation. If you know engineering, mechanical engineering like that, yeah, this would be the potential energy and the kinetic energy components. So again, we can step through making sure that this is a natural Lyapunov function or a candidate. So first we want to check that V of 0 is equal to 0. So cosine of 0 is 1, 1 minus 1. For this part, cosine of 1 I'm sorry, cosine of 0 equals 1. 1 minus 1 is 0, so this part is equal to 0. X2 equals 0, x2 squared equals 0. So that means it has x equals x1, x2 equals 0, 0, v of 0 is equal to 0. So this part checks out. The next thing we want to check is that v is radially unbounded. So namely, v of x goes to infinity as x goes to infinity. We can check here. So this first component is bounded, right? So this first component is bounded. However, this component is unbounded, right? So as the norm goes to infinity, or x1 and x2 go to infinity, this also goes to infinity. And lastly, we want to check that v of x is positive, semi-definite. Oops, not v. Great, positive, semi-definite. So we can do that by just, again, do the same argument. Cosine of x1, or cosine in general, the domain of cosine, or the range of cosine for any domain, is in between -1 and +1, right? So that means that this first term here is always greater than or equal to 0. This term here is x2 squared. So for any x2, then this term is also positive. So this implies that v of x for any x1 and x2 is also positive. Right, so that checks out. All right, the last thing to check is check the derivative of v. Okay. Great. Okay, so sorry, just looking at the example really quick. All right, so the derivative of v, this guy is equal to, so we'll take this whole quantity, a1 plus cosine of x1 plus 1 over 1 half x2 squared, and we're going to do this whole thing, and we're going to take the derivative of this. Okay, so what is that? This will give us a1 minus 1 plus, where'd it go? Yeah, plus the sine of x1 plus 1 half x2 times 2. And this will be times x2 dot, and then this will be times x1 dot. And I'm missing something. This guy goes away. All right, so let's move this over. Make sure that conforms with what I got here. Yes, okay, great. So this guy is equal to, and there should be an A. So this guy conforms to, is equal to a x1 dot sine, let's do it this way. Sine of x1 plus x2 dot. Okay, so now let's plug in x1 and x2. Okay, so again, x1 and x2. So we'll get a, and then x1 is equal to x2. x1 dot is equal to x2 sine of x1 plus x2 times minus a sine of x2. Okay, so this guy is equal to 0. Okay, so now what does this mean? So we have v of x dot is equal to 0 at the end. This doesn't conform with the properties that I told you before, right? Where we need to have decreasing a v dot. Sorry, we have to have a decreasing Lyapunov function. In fact, what this shows us is if we have v dot equal to 0, this shows us that solutions do not converge to the origin. However, they are bounded which implies that we can find that epsilon for any delta that we bound our solutions to. We can find that epsilon, which is in this case equal to delta, such that our solutions stay within that epsilon ball, right? So we can conclude. And we can conclude that solutions, or that the origin is stable. Also, like I mentioned, since the derivative of v dot is equal to 0, we can, which again means that the energy does not change over this, because our Lyapunov function is the energy equation of our system. We can show, this shows us that the energy doesn't dissipate, right? So we can also conclude that the origin is not, right? Because we don't have convergence, the origin is not asymptotically stable. And lastly, for trajectories starting on, say, what quote unquote a Lyapunov surface, which is basically the set of points v of x is equal to c, where c is some scalar. C is some scalar greater than 0. They remain on that surface. Okay, so now what happens if we start at the origin, right? So that would be c equal to 0, which means that v of x is equal to 0 for all future time, which means that the solution stays at 0. Okay. Likewise, if you start at with some position in your let's see, if you start at some position, say offset from 0, so we started here, theta, then because there's no frictional forces, you're going to oscillate between those two, you're going to oscillate forever without dissipating any energy. Okay, so and again, this is from, just write it up at the top. So this is from, oops. Example 4.3 in nonlinear systems. Third edition by Khalil.